All right, implicit differentiation is where we don't have to explicitly solve y is equal to f of x and then differentiate both sides with respect to x to figure out what the derivative of y with respect to x is, right? You can just leave all the variables x and y jumbled up together and differentiate all at once, which is a good thing because we would not be able to solve this equation for y. So we'll differentiate the entire equation. X squared y to the fifth minus 3xy plus 5 is equal to 0. So when we differentiate the entire equation, we can take advantage of linearity and differentiate each piece separately. In fact, let's go slow through this at first. There we go. We'll differentiate the x squared times the y to the fifth first. Subtract 3 times the derivative of x times y. And add 5 times the derivative of a 1. I guess I could have left the 5 right there. But either way you want to think about it. And the derivative of 0. All right. So this first derivative, notice you have a product of two things, x squared and y to the fifth. Now it's tempting to treat that y to the fifth as just a constant as far as x is concerned. But the y is trapped in that equation with x. So if you change x, y has to change too. So y depends on x. So the derivative is not going to be a constant, or rather it's not going to be 0. Y is actually not a constant as far as x is concerned. So we actually do have a non-trivial product rule. And when we differentiate that product, we get the derivative of the first term times the copied second term plus the copied first term times the derivative of the second term. Now, notice what I just did there. When you differentiate with respect to x, remember, this is the derivative with respect to x, y to the fifth, it's a chain rule. You first have to differentiate y to the fifth with respect to y, right? You have to differentiate something is being raised to the fifth, and then you have to multiply by the derivative of y with respect to x. Right, so this part is the derivative of something is being raised to the fifth, right? 5y to the fourth, and then dy dx. Let's use Newton's notation, understanding that all of the derivatives at this point are with respect to x, right? So that y prime is just dy dx. Okay. Now, where are we? That's just the derivative of that product. Now we have minus 3 times the derivative of x times y. So again, we have a product rule. The derivative of the first, so the derivative of x with respect to x is just a 1. Copy down the y, add, copy down the x, and the derivative of y with respect to x is exactly the thing that we're looking for. That's y prime. We add 5 times the derivative of 1, but that's just 0, and the derivative of 0 is 0 as well. All right, now that we've taken all of our derivatives, let's clean this up. This is 2x times y to the fifth plus 5x squared y to the fourth y prime minus 3y minus 3x y prime is equal to 0. Okay, let's remind ourselves of what we're trying to do. Give the instantaneous rate of change in y with respect to x. I'm looking for dy dx. Right, I'm looking to solve for y prime. So let's take that relationship that we just gave ourselves and solve that for y prime. So let's leave everything that has a y prime on the left-hand side of my equation, and then everything on the right-hand side, we'll throw everything that doesn't have a y on the right-hand side. So the 5x squared y to the fourth y prime is staying on the left. The minus 3x y prime is staying on the left, but I'm going to move over the 2x y to the fifth and the 3y. All right, now both of these terms on my left-hand side have a y prime by design, so I can factor that out. In fact, instead of writing minus something plus something, I'm going to write it as 3y minus 2x y to the fifth. I just don't like to have leading negatives. And then now get my y prime by itself. I divide by this parentheses. So y prime is equal to 3y minus 2x y to the fifth divided by 5x squared y to the fourth minus 3x. So notice implicit differentiation, because you can't write, or rather, when you can't write y as a function of x, you have to use implicit differentiation. And in fact, the slopes of the tangent lines depend, look at that equation, not only on x's, but on y as well. So it's going to change your graph of not the function, but the graph of the equation might not be a function, and the slope here at this x value is different than the same x value slope. You just have two different y values.